Okay, so here's like a continuation onto the previous video, which was showing how we can do a design problem for based on fatigue. And I did this Shigley problem 619. Now I'm going to do it in redo it in Excel. So here was the problem, and you can go see the video where we were able to get the moment that we cared about and then enter in all this stuff right here. Some of the things that we had to do, though, were make an assumption about the diameter, especially right here. We also had some things about the fillet radius that we had to make a decision, but it's really the diameter. So I'm going to make a Excel spreadsheet tool that we could possibly reuse or at least modify to try to do this problem. So I'm going to start entering some of the things that we know. We knew that there was 120 was the ultimate strength, and it was KSI in this case. The bending moment that we were going to use, let's go and enter it in instead of, we could set this up and so that we could like maybe put the force in there and all the arrangements of the stuff, but if you wanted to, but it ends up making it maybe a little too specific. The smaller diameter, let's just pick out some numbers. Let's say, let's pick out that it was like 3. And the larger diameter, we can say that it's going to be 1.4 times that 3. And usually what I use these colors for are inputs, right? So I'm going to take this color out for there. And the fillet radius, that was also kind of decided for us based on the original problem. You could see that we had D divided by 10. So we'll go ahead and keep that up right there. And so we'll set, instead of having this be an input, we'll follow along with the problem. Operating temperature, it doesn't matter to us in this problem right here. So we probably won't even bother with it. I could probably get rid of that line. So right here, we know that we have 120, and we'll multiply it by 0.5 for the rotating beam endurance limit. I forgot to put in units into this other thing, so let's put those into there. I will delete this one. I'll delete it and then move everything up. So delete and shift it up. All right, that's cool. All right, so don't hurt anything. And A and B, this is going to be the A and B. Oh, by the way, I'm going to get rid of that label. This is going to be the A and the B that comes from the book based on the surface condition factor. And that surface condition factor, I use the 11th edition for this, so we're going to have a slightly different thing from the 10th edition. But I looked it up, and we had 2.0 for that A and a negative 0.217 for the B. And so this ends up being that times this raised to this. Boom. And so that's what I got. So it confirms. Now this is rotating, so we don't actually need this line right here in this case. But if it had been a non-rotating, or it had been like a square section, we would have the equivalent diameter, and we'd use that for the size factor. The size factor should probably be an if-then statement, because if we had something that's larger than 2 inches, we use one equation. If something smaller than 2 inches, we use another equation. I do believe that I assumed that it was going to be the larger of the two. All right, so that's what I did. Yeah, I said that it was going to be between 2 and 10 inches right in there. So we might do an if-then statement to be careful to make this more useful to us. But I'm going to go ahead and assume that it's going to be larger than 2 inches and use the 0.91 d raised to the negative 1.57. And you could have also made all those values into into it as an input if you wanted to. I mean, you can. There's definitely a bunch of different variations that you could do in making this spreadsheet. But let's see, we're going to go times to 3 inches, and we're going to raise it it needs to be raised to a negative number, so I need to put a parentheses in there, and we'll go minus 0.157 close parentheses, and we got something a little different than what I got. So I might have made it like a numeric error, 0.91. Oh no, I know why, because I assumed 2 inches, I think, when I was doing mine. The load factor, this is 1, 1, and 1. And even this one, miscellaneous factor, that's not even in the 11th edition anymore. So what you do is you go this times that times that times this times this. And we don't even, this is kind of unnecessary to some extent. I mean, at least for this version, because we used 1 everywhere, but we got the value. We can put an equation in for this now. Might as well, for the, if we're going to make a spreadsheet that's going to be useful to us. So this is based on this graph, but now in the 11th edition we have this right here. We got to be careful that we don't go over 200 or under 70 for this equation, but we can make sure that we have it. We could put like a little star next to it. I think usually use orange for stuff that I might want to change, right? I usually use the yellow for inputs, and that one actually, this one maybe should be an orange as well, because it depends on what this was. This was for machined, that A and that B. So I'll put in that equation, and that's 1.06 minus 2.8 E minus 3 times ultimate strength, boom, plus 6.9 E minus 6 times ultimate strength squared. And I should get pretty close to right there, 0.82. I think in 0.82 was what we had on the graph. Remember, for 120.82. So I guess they decided that their curve fit was close enough, I suppose. So anyway, so now we got this. Now we can enter in what our A and our B are going to be. Those are equations from right here, right? That A and that B. F's times the ultimate strength squared divided by SE, and minus negative 1/3 log base 10 of F SUT divided by SE. So put him into place, equals, and the quantity, this times that, close squared, and divided by that. Boom. And then B is going to be equal to negative 1 divided by 3 times LOG. And then we're going to take F times SUT divided by SE and close. Boom. And I already had this arranged up here, so it would show what the fatigue SN diagram will look like based on these values right here. I have like little if-then statements and that kind of thing to show up. Fillet radius for use here. So this is actually maybe something we want to make as an input. We don't want polar moment of inertia. We just want moment of inertia for this one. So we don't know this fillet radius right here. We could set it actually equal to this one right in there. All right, so let me get rid of this as an, that's why it was not an input. I is going to be equal to pi divided by 64 times, and then this diameter fourthed. Is that right? I think so. I think I got that right. I didn't need that. I don't know why it has this. I guess I'll put it there. That times. Oh no, I do. I guess I do need it. That times SUT. Boom. And d over d. Well, that's actually already done for us. D over d. Yeah. 1.4. And then r over d. It's kind of silly to have them there. R over d. That's right. Boom. 1/10. And then nominal stress amplitude, and this is actually we insert and put a sigma in there instead. Where'd you go, sigma? Have I not used sigma recently? Here, I'll put up sigma in. Get rid of my tau. All right, so this is alternating. So that's going to be equal to my m times my diameter divided by 2 divided by my I, which seems too high. Wait, what happened? Boom. Yeah, that seems pretty high. I'm a little nervous about my I. Pi over 64 divided by times that fourth. Okay, must be because it's so large. It's a big number. Okay, so my KT, I'm going to look up. I'm just going to go ahead and use a number that I had gotten, but this is one that is based on the ratios and how I read them. You know, this 1.4 and this 0.1. I think I showed that in the previous video, and I ended up getting for 1.65. All right, so now it's now that we're making a spreadsheet, we might as well go ahead and put in the notch sensitivity factor, which does have an equation. It's sort of a pain. It's for whatever reason they do this square root of a thing, but it's not terribly difficult to do, but just sort of a pain. And so, so for an ultimate strength between 50 and 250, which is just about everything for us, we're going to find a square root of a, and then we put him into this Q right there. All right, so this is a bunch of boring things as we go through, but just bear with me as I enter in these equations. And so what we have is square root of a is going to be equal to 0.246. In fact, actually, I could do something here. Let me see if I have the copy of Shigley, and I could just put the, sometimes it helps to have the thing right in front of you. So let's see, where's the Q? There you go. And I think they're the same between the 11th edition and the 10th edition. This is the 10th edition. Boom. This is a exciting video. Makes for exciting videos, right? Exciting videos. So there you go. There's yes, equals 0.246 minus 3.08 e minus 3 times that, okay, and then plus 1.51 e minus 5 times this squared, and then minus 2.67 e minus 8 times e minus 2.67 minus 8. I think I get that times this cubed. So I did a cubic curve fit onto there. Hard to say if I got that right or not. I could, but let's see if this Q will tell us if we get it right or not. And so the equation to use for this is right here. Right, so we say that Q is going to be equal to, 1 divided by the quantity of 1 plus the square root right there, divided by, now you actually have to use the square root of the thing. And they're just calling this thing square root. I don't know why they do that. It must be a really good reason. I'll put it right up in there, and boom. And then I think we're done with that. All right, so we get 0.9199. And we have to double check later on if that's going to be a correct thing. We say equals, though, for the fatigue stress, right? The fatigue, saying everything wrong right now. Oops. There you go. For the fatigue stress concentration, it's going to be equal to 1 plus Q times the quantity of that, you call it theoretical stress concentration, minus 1. Close. Boom. 1.598. That's in the range of what I expected. I might need to look at that a little bit more closely. This one I'm going to change this into sigma. It was tau, right? And so I'm going to take this equal to that times their nominal. Boom. And, you know, I like to make these into KSI, and I've neglected to all the way along. So here, so let me put in units everywhere that this serves it. So that's in KSI. That should be inches. This should be inches fourthed. I guess that is technically in KSI, so sure. And this is KSI. And we need some more units. We need some more digits. Let's put this in here. Boom, boom, boom. And yeah. And so now the life estimate, what we're going to use is go backwards and use the equation. Where'd you go? There you go. Right here. Right, so here's the equation that we use, and that's going to have equal reversible stress, it's just this one right here, at least that's what the 10th edition calls it, divided by A, which is up here, and raised to, careful of this, 1 divided by B. And whoa, that's, you notice, okay, so one thing you'll notice is that that's way larger than, yeah, I guess I can leave it as, I like to have, there you go, boom. All right, so there you go. You can see it's way larger than 1 million. And I even have it plotted out here. That's because it's underneath the endurance strength. So we could, the usefulness of this is that we could now change this diameter, right? So we could say, well, what happens if it's 1.5? Boom, you can see how much it went to almost low cycle fatigue. 1,283 cycles is what we could say over there. I didn't finish the labeling of this KSI, right? But this is cycles. And so here is the magical portion of this. We're going to go to data and the what if. What if is very useful. And the thing called goal seek. And goal seek is a very useful design feature that you can do in Excel. And what we say is very simple. We're going to set a cell. Let's set this cell right here to 100,000 by changing the diameter. And all it's going to do is just go boom, and it's going to figure out that in order to make this thing die, whoops, I didn't hit accept. I think that's what happened. Goal seek, do it again. Set this cell to 100,000 by changing this cell and say OK. And so there you go. It found that was going to be 1.860. So what was I trying? Well, I was trying for 570,000, right? So let's try for 570,000. See how we get. Right? We did we kind of wrote the equation backwards to get this, but this is a nice way instead to do it instead, because what you could do is you could take an analysis and you could turn it into a design tool as opposed to rewriting the equations out again. I get rid of these guys. Now, what you want to make sure, though, is when you set this thing up, you've got it set up correctly. But what it did is it figured out the size factor. That's one of the nice aspects. But that's not going to be correct because this is out of the range of that size factor. So it might have been better to have an if-then statement in there, and that might mess with your setup here. But let me go and change my what if thing again. So we got a what if and goal seek. And now let's change this to 500 and, oops, there you go, right there. We're at 570,000, 570,123. And that's going to be by changing this diameter. And we say OK. And so you can see where it lands on my log scale, on my SN diagram. And you can see that at 2.049. And by hand, I got 2.032. One of the primary differences, is going to be that KB. We also might want to go back and reinvestigate. So we might want to pick, like, what is the effect of just being 2 inches instead? Well, that's a pretty big jump from our 570,000. We have 362,000. And recall how I'd only want you to give 2 sig figs when you report a life of something, because it's not, this is way too specific. You could see, but this is a small change, how that affects what the results are going to be. I think I'm done. I think I'm done trying to show you what you could do with this design tool and how useful that goal seek is to try to come up with a solution to something. We might be able to, but by messing with the safety factor, not safety factor, the stress concentration, but that's going to be kind of tough. We also, one of the things that was different in here, we could try to change this notch radius, right? We could try to go 0.15 and see what happens. The only thing that's going to affect in this is going to be the Q, so it's not going to affect. It's not going to be changing what the stress concentration is right here, and that stress concentration, as you remember, was based on the ratios that were getting used between that were based like right in there, because that's what was given to us in the problem as a suggestion. So. I think I want to go back to the goal seek and leave it to this diameter. Now, interestingly enough, the solution that Shigley has provided for the 10th edition, well, of course, that's the 10th edition, and I'm using 11th edition parameters. So that wouldn't be right. But anyway, they don't seem to even be following their own problem. And I never looked closely. I can't see where they've used their safety factor anywhere. Because in the original problem, I decided to deviate from the original problem and not use the safety factor. But I can't find where they did anywhere in here. And I keep looking for it. And I don't find it. So, an interesting thing. Immediate results are, well, anyway, that was this is sort of the big idea behind the thing, and hopefully you will be able to do the homework problem. But you didn't really need to do this Excel thing to do the homework problem. This was just a plus bonus added thing.